now you should have a good idea about using the shortcut approach to analyze the frequency response and to sketch the body plot of a circuit, right? Okay. And today, I'm going to apply that approach to various amplifiers, BJT and FET. Yeah. The example I gave you last time for RC circuit. Okay, that's too simple, right? So we're going to go to the amplifiers. Okay, so let me review again the basic concept of this shortcut approach. Okay. Okay. So basically, when you try to use this approach to analyze the frequency response of a circuit, what you do is first you can derive and calculate A sub B max, right? And when you do this, you assume the C in series is short and C in parallel in the circuit is open. So sometimes it's called a A sub B ideal. Okay? And as far as this is concerned, we have learned it before, right? Correct? We have done that in the previous chapter. In the previous chapter, that's all we did, right? Okay, second, you will have to derive and calculate the corner frequencies associated with the capacitor. Okay. And once you have done that, oh, by the way, if you want to use this approach, one condition must be met. Okay, so what's the condition? The condition is that C in series is large and C in parallel is small. So how large is large? Typically, this has to be in the neighborhood of microfarad, and this is in the neighborhood of picofarad. Okay, so that's the condition. And then once you have done that, then you can sketch the body plot. So basically, you will have a plateau, right, in the middle, and that is what we call the A sub B max. All right, and then whenever you have a C in series, it will introduce a corner frequency in the low frequency range. Low frequency range, got it? And whenever you have a C in parallel, it will introduce a corner frequency in the high frequency range. Yes, got it? So this is caused by the C in series. This is caused by C in parallel. Yes? Now, of course, this is what we call the corner frequency, omega low, omega high. Yes? And this is the bandwidth. Now, if you have more than two capacitors, what do you do? Let's say if you have two CS, two CP, yes? Then you would have something like this, you have something like this, yes? So this is the second CS. This is caused by the second CP. Huh? And the slope, the first drop is always what? 20 dB per decade. The second drop is always 40 dB per decade. Huh? So depending on how many capacitors you have, then you would have the same number of the polar frequency. So that is the concept. Yeah? It's not difficult, right? So now I'm going to do examples. So some people ask me, are we going to do bipolar or do the FET? Well, unfortunately, we have to do both. Okay? We have to do both because we have learned both before, right? As far as the exam is concerned, I would have to choose one. Yeah? But as far as the learning is concerned, you have to know both. So I cannot tell you which one you're going to have on the exam because if I do that, you're going to you know, right? Yeah. You're not going to learn the other one. You're going to just learn this one, which is not good. Okay. But when it comes to time for the exam, maybe, I'm not sure, okay, maybe I will tell you which one.
That'd be appreciated.
Huh? Okay. I'm not sure I can promise I will tell you that, but I may. Right? But now let's try to learn both, okay? Before I get started, maybe I should give you the homework assignment. It's not going to be due until the last class of the semester. You know what's the last class for us? I look up the calendar. It is not December. It's November the 30th, which is Wednesday. Okay? That is the last class for us. So here's the homework assignment, homework number 7. Okay, so it's due on this day, okay? And then you know your final exam schedule? Hmm? Yeah.
I know that you were saying the final exam would be on the last Wednesday, but I looked up the time for this class was on the first Wednesday. Yeah, it's on the 7th. Right.
It's on the 7th. That's the final exam for the class.
Right, but basically, like, I thought you were saying that it was going to be on the last Wednesday of finals, but it is the last Wednesday.
Yeah.
Isn't that the
Which is a Wednesday, right? Your final, the final will be on December the 7th.
So it's the week of exams, then just the 1st through the 7th?
Well, this week is the final exam week.
Tuesday and Wednesday?
Yeah. And your exam will be on Wednesday. Okay? I think it's from 10 to 12 or something.
Yeah, it's 10 to 12.
Yeah.
Will it be the length of the other exams?
Huh?
Will it be the same length as the other exams?
I have not decided yet, but most likely it will be 1 hour and 15 minutes or 1 hour and a half. Maybe. Okay, good. So if you're going to do well in the last exam, the next few lectures, including today's, will be very important because I will do a lot of examples. And also, I really encourage you to do the homework, okay? Without looking at the solutions. I know the solutions are around somewhere, okay? But you should try to do the homework yourself, okay? So I cannot force you, but it's for your own benefit. Okay, so let's do this example first. Start something simple. So this is a BJT amplifier. Maybe you have forgot about BJT stuff, huh? I hope you do not. All right. So basically, I want to find out the Bode plot, okay, the frequency response of this circuit. All right. So there are lots of values I have to give you. R1 equal to 12.8K, R2 2.4K. Okay. What's this? C. All right. VCC 10 volts. Beta is 100. Okay, that's all we have. So doesn't matter what you do, right? The first thing you have to do is to do the DC analysis, correct? Okay. I hope you still remember how to find DC, huh? So let's say this is VR2, can I? So let me do this one more time for you, okay? So VR2 is VCC times R1 plus R2 and R2, correct? Okay, and then you go around the loop, right? That's what we call input loop, yes? So VR2 equal to VBER, yes? Plus ICQRE, right? Remember, this is ICQ, right? That's ICQ as well, yes? Okay, and then plus yeah, that's it. But I think I need to add one more term. That's IBQR7, right? Remember? Because in the DC analysis, this is what you have, right? And this is called V7, which is the same as VR2, correct? This is R7, yes? So you go around the loop, that's what you have. And then from here you can calculate ICQ or IBQ, doesn't matter which one, right? Okay, so at the end, you can find that ICQ is about equal to 2 milliamp. All right?
R7 is what RS plus R1.
Well, yes, R1 in parallel with R2, right?
What about the other resistors?
Yeah?
The other
R3.
Because capacitor is a liquid acid or something, so you don't have all that.
Huh?
It's not gonna have resistors.
Yeah, well, by the way, if you forgot about it, go back to the BJT chapter to refresh yourself. Yeah? Okay, now let's do the AC. Yes? Again, a very important component of the AC analysis is the equivalent circuit, right? So go from left. Yes? And then it's connected to the base terminal of the BJT. The emitter is connected to RCB to the ground. Yes? All right. And the collector is connected to R sub C to the ground. Yes? And that is where we have the output terminal. Okay, then, so this is the BJT model, correct? For the BJT model, you should remember there's R sub pi here, right? And then there's a current source, which is called beta I sub B, yes? This is I sub B. Okay, so that's it. Now remember, R sub I is a function of ICQ. I forgot the formula, right? You can find it somewhere. Yes? So that's why you have to calculate ICQ first. Otherwise, you do not know the value of R sub I. Yeah?
Shouldn't that capacitor be shorted?
Huh?
Shouldn't that capacitor be shorted?
Capacitor be shorted? Not yet. Not yet. Okay, but this is the complete, right? Including the capacitor. Okay. So now, if you try to calculate A sub B max, then yes, the capacitor will be shorted, right? So C is shorted. When calculating A sub B max, okay? Okay, so let's do that, right? So now if you short this guy, yes? What is V sub O? V sub O is equal to beta IB minus times R sub C, correct? Okay? And what is V sub I? Well, this guy is going to make it more difficult, huh? So what I can do is the following. I can say this is I sub I, right? Okay, I sub I. And let's say this resistance from this two terminal is RIB, can I? And let's call this resistance from here is R sub I. Huh? Can I? Okay. So what is RIB? I told you the shortcut before. RIB is simply R sub I plus the weighting factor multiplying to R sub B, correct? And the weighting factor is always what? Beta. Okay? So therefore, R sub I is simply what? R1 in parallel with R2 in parallel with RIB, correct? Okay, so therefore this is what you have. Okay, this is RIB, this is R1 in parallel with R2, correct? And this is R sub I, and this is I sub I, yes? Okay, remember, the current going through this is what? I sub B, yes? And this is V sub I. Yeah? Okay. So there's a relationship between I sub I and I sub B, right? So I sub B is basically a portion of I sub I, yes? So it's what? That is determined by the current divided rule, yes? So R1 in parallel with R2 plus RIB, and then R1 in parallel with R2 on top, right? Okay, so therefore, I sub I is I sub B times R1 in parallel with R2 plus IB. Okay, so why am I doing this? Well, because this can lead to the expression for V sub I, okay? So V sub I is equal to what? Is equal to I sub I R sub I, yes? Plus what? Yes, plus I sub B times RIB. Yes? Correct? So it becomes here, huh? V sub I is equal to the body drop here, right? Which is I sub I times R sub I plus the body drop here, right? And this body drop is I sub B times IB, right? Another way you can do is you can combine the two, and V sub I will be equal to I sub I R sub I plus why am I having R sub I? 2R sub I. Oh, gee. I don't want to confuse you. Huh? So let me change the name, can I? Can I call this R sub S? This should be called R sub S, okay? R sub S. So this is R sub S. So this is R sub S. Okay? Got it? And this is R sub I. So V sub I is also R sub S plus R sub I. Okay, that's the same, isn't it? Because the combination of these two is what? Is R sub I, yes? You can combine the two, yes? That becomes R sub I. So V sub I can also be expressed as I sub I times these two are in series, right? So that's the same. You know, you can do this one, or you can do this one. It doesn't matter which one you do. Okay, so this, if you use this one, then is I sub B R. This is R sub S. Huh? Okay, so I have to correct this. This is R sub S. Yeah. So I sub B R sub S times that. Yes. It's a lot of algebra. Okay, plus I sub B times RIB. Yes. Okay, so that's V sub I. Why am I doing all this? Huh? Because I need an expression for L V sub I as a function of what? As a function of I sub B. Got it? Because V sub O is a function of I sub B. So therefore, A sub B max is equal to V sub O, which is minus beta I sub B R sub C on top, right? And then V sub I on the bottom. So I sub B cancel, right? And then R sub S. Take a lot of time to write this. Okay, so that's the expression of AB max. Now you can plug in the numbers, yes, right? So you can plug in the numbers and let me see what it is. I don't know the real number, but I know the number in dB. Okay, so let me give you that. So 4.5 dB. So that means you have that value, right? Then you do the 20 log 10 of the value. Then you get this number, yeah? 45. Okay. You know, this stuff, AV Max, we have done that many times, right? So I don't think I can spend too much time on it. Now, let's talk about finding the corner frequency, right? So there is a time constant associated with the capacitor, right? Okay, tau associated with capacitor is called the RC time constant. Yes. So if you look at C, right? C, and you look at what is the equivalent resistance on the left hand side. What is it? It's R sub S, right? Because when you try to look for the equivalent resistance, this is shorted. Yes, this is always shorted. Okay, so you have R sub S on one side. What do you have on the other side? Huh? R sub I, correct? Right here, R sub I. So therefore, you know what's R sub I, right? R sub I is R1 in parallel with R2, right? In parallel with RIP, yes? So therefore, tau sub C is equal to C times these two are in series, right? R sub S plus R sub I. And omega associated with the capacitor is 1 over tau sub C. So if you plug in the numbers, you will find that omega is about 50 radians per second. So that's it. So now if I plot, right? If I plot A sub B versus omega, so this is 50, right? This is AB max. Right? That's it. So AB max is about 4.5 dB, yes? And this is 50. So that means for this type of amplifier, if you put a signal at the input terminal and the frequency of the signal is less than 50, then that signal will not be able to be amplified. Yeah? Because of the big drop below 50. If you put a signal at the input terminal and the frequency is larger than 50, then it will get amplified. Yeah.
So you said a good design is to just have as few capacitors as possible to kind of make it more linear response, correct?
Yeah. Well, imagine if you have 0 capacitor.
It would be a straight line, yeah. But
you could have a constant A sub V for all frequencies, which is perfect. But never have that.
now, did you say that you can use less capacitors, but doesn't it make the math for like multi-stage amplifiers just more difficult?
Well,
Or is it impossible to go without any?
no. For example,
Mm.
you must have a capacitor here, right?
Right.
Otherwise, under DC condition, this is short. This terminal will go to the ground,
Okay.
right? So this capacitor is.
So it has to be there no matter what.
You must have it.
Got it. Okay.
And also later on, we're going to have to talk about the capacitor embedded in the transistor.
Is there capacitance or like an actual capacitor like as part of it?
It's capacitance.
Okay.
So that is also there.
Right.
You cannot get rid of that.
Okay.
So
So no matter what, it's gonna have.
you always have some capacitance.
Mhm.
Yeah.
What are the units of omega C?
Omega is a radian per second. You can sometimes the problem will actually convert to the frequency in hertz, right? You know how to do conversion, right? Yeah, omega is equal to 2 pi f, and f is the frequency in hertz. Huh? Okay, so let's move on. Huh?
When graphing A sub B and omega, you knew it dropped on the left because the capacitor was in series.
Yes, as I said, whenever you have a capacitor in series, it always introduces a corner frequency in the low frequency range. Right here, right? It's the low frequency, 50, right? So then, if it's in low frequency range, it will drop this way. In the high frequency, it will drop the other way.
Okay. So if we had, say, a bypass capacitor on RE, that would make a band pass.
Well, if you have a bypass capacitor, unfortunately, this shortcut approach does not apply. And I will show you why later, not today. Yeah. So if it does not apply, then unfortunately you have to what? You have to use the conventional approach, right? So basically you have to look at the circuit. You will have to derive the transfer function, which is a function of S, right? And then you have to use the Bode plot approach to sketch the Bode plot. That will take much longer. Yeah. Okay, so that was a BJT. I know you like to do a FET. Okay, so let's do a FET. Okay, and okay, so this is the circuit, and we want to find out what is the value of C, so that the corner frequency is 10 Hertz. Right? So basically you need to design this capacitor so that you have a corner frequency of 10 Hertz. All right. So tau associated with C is equal to C times what?
Resistance C by the factor.
So if I look to the side, let's call this R out, right? So it's what? R out in parallel with R sub what? L, right? Agree? Huh? So basically you have C here. On this side you have R out, right? On this side you have R sub L. Oh, I'm sorry, not parallel, huh? What?
Plus.
Plus, yes. Okay. And what is tau sub C? Tau sub C, according to the information we have, so tau sub C is equal to 2 pi f sub C, right? And f sub C is 10. So it's 2 pi times 10. Yes? I'm sorry, no, I'm not doing this right. Omega C. Yes? Omega C, which is the corner frequency in the unit of radian per second, is equal to 2 pi fc, and fc is given 10 Hertz. Yes? Okay. So tau sub C will be equal to 1 over omega C, so it's equal to 1 over 2 pi times 10. Correct? And that is equal to C R out plus R L. So that is the equation. RCL is known, but this guy we do not know, right? So as soon as I can find out the value of R out, I can calculate the C. Yes? So how do you find R out? Well, you have to look at the AC equivalent circuit, right? So basically, let's do the AC equivalent circuit, okay? V sub I R sub G, right? That's the gate. Okay, and the source is R slash to the ground, yes? The drain has R sub D to the ground, yes? And then you also have R sub L to the ground, yes? So that's the C. Correct? We have done this many times. Huh? And then this is the model of the MOSFET. So then all you have is a G sub M VGS, right? So it's a VGS. Okay. Now, what am I looking for, by the way? I'm looking for R, right? So therefore, what do I have to do? I have to apply a test voltage, yes, at the output terminal, and then this becomes disabled, correct? R sub G, R sub S, R sub B, right? So then I'm going to apply a test voltage, V test, and this will generate I test, correct? So here's between here and here, that's VGS, right? Okay, so R out will be V test over I test. Yes? So this is the R out right here. The output resistance. All right? So if you look at the node here, right? I test equal to V test over R sub B plus GM VGS, correct? Yeah. This is KCL. Okay. Then I go up here. Then if you look at this plus that equal to what? Equal to 0, right? This plus that, yes? Equal to 0. So VGS plus the voltage drop on R sub S, right? This plus that. The voltage drop on RS is what? GMVGS times R sub S equal to 0, yes? According to KVL. Again, this is the voltage drop, on RS. Okay. Then the only solution for VGS is 0. Correct? Because if you have VGS on one side, the other VGS times a constant, right? Because this and that is a constant. How can you make these two equal to each other? There's only one solution, VGS equal to 0, right? So you have 0, 0, then both sides 0. That's good. If you have anything other than 0, For example, if you have 1, this is 1. So how can 1 equal to 1 times k, right? It's not possible. So the only solution which is 0. Okay, so that is 0, right? So then what is R out? You put this here, right? Then R is simply R sub D. Got it? So now I come back to somewhere. Huh? Come back to here, right? So tau sub c is what? 1 over 2 pi fc, which is 1 over 2 pi times 10, equal to c times r out. That's derived r sub d plus r sub l. Yes? So there's only one unknown now. So c is 0.95 microfarad. All right. Now, if I ask you to do the sketch the Foley plot, then what do? Then you have to try to find A sub V max. Yes? Okay, why don't we do that quickly? Huh? A sub V max. So this is V sub L. Yes? When you do A sub V max, this is short. Yes? So V sub L is minus G sub N VGS R sub D in parallel with R sub L. Correct? Right? These two in parallel, and there's a current G sub N VGS. What about V sub I? V sub I is this, right? This is this plus that, correct? VGS plus GM VGS R sub S. Oh, so that's good. So this is in terms of VGS, this is in terms of VGS. So I can find A sub V max by dividing the two, right? Minus GM RD in parallel with R sub L over 1 plus GM R sub S. That's it. So you get a value, right? I don't know what's the value. And then you take the 20, then you take the 20 log 10 of the value. Okay, then you can put that value here, right? So that's the A sub V max. And then, what is the corner frequency? Huh? It is what? 10 hertz, right? That has been given. So that's the Foley plot. All right. So the two examples I just did. Each one has just one capacitor. So now let me do an example that has two capacitors. Huh? Okay, two capacitors. And I will start with the BJT. Okay. then we have RSL to the ground, which is 10K. And we have a C2 to the ground, which is 15 picofarad. So that's where you have the output terminal, okay, E sub L. Good. Okay. So apparently you're going to have a corner frequency in the low frequency range coming from this one, right?
Mm-hmm.
You have a corner frequency in the high frequency range coming from this one, yes? So you should expect that the body plot will be like this, a plateau in the middle, okay, and the drop on both sides. Yeah? Of course, the question is, what is the value of the plateau, right? And what are the value of the two corner frequencies? That's all. Okay, can I skip the DC? Huh? I've done it many times. You know how to do it, I hope. Okay, so let me skip the DC, can I? Okay, so you need to know how to do the DC, right? So from the DC, you can find ICQ, correct? Okay. And then you will have to do the AC analysis. So let's go and do that.
Do you have that ICQ?
Let me check. Yep. It's 1 milliamp. Okay, so you go home and go through this and make sure that the ICQ you found will be 1 milliamp. Okay, so this is R slash. This is C1, right? Okay, then this is the base terminal. Then the emitter, R3 to the ground, yes. This R1 in parallel with R2, yes. The capacitor, R sub C to the ground. And then you have R sub L to the ground, yes? Yes? And then you have C sub L, C sub 2, whatever. To the ground. Okay? So then here's the model for BJT. Beta, I sub B, this is R sub I, so this is I sub B. Yes? So R sub I is, according to the formula, R sub I equal to beta BT over ICQ. So ICQ is 1 milliamp, as I told you. So R sub I will be 2.63. Okay. Okay. Can I also skip AV max? This circuit, if you try to do AV max, this is short, right? This is open, correct? Then this is almost the same as the circuit I just did. Yes? What's the difference? What? Correct? I just did it this way just a while ago. Okay, so let me skip that, right? So then you can find AV max. I can give you the expression. So AV max equal to beta RC imperial with R sub L times R1 imperial with R2 plus R sub I times 1 over okay. Probably just the same as the one we derived from the other example. Okay. Now what is R sub I, right? This is R sub I right here. Yes? So R sub I is R1 imperial with R2, imperial with RIB. Yes? So this is RIB. So RIB is R pi plus the weighting factor beta times R sub E. Yes? Okay. So I have a value for that about 6. Okay, that's the value, the real value of AV max. And I have a value for R sub I as well. It's 53K. Okay. Yes.
You said R sub I is 6, and then R sub I is 52K.
RIB.
Huh?
AV max is 6.
This is R sub I, this is RIB.
Oh, you're saying AV max is 6 there? Yeah. Okay.
Oh, AV max. Yeah. AV max. This is separation, okay? All right. Now we have to find the two corner frequencies, correct? Okay. So if you look at C1, so C1 on one side you have R sub S, on the other side what do you have? R sub I, correct? So this is R sub I, yes? So therefore, tau associated with C1 is C1 times R sub S plus R sub I, yes? And that value for that is 4.7 times 10 to the minus 2. So therefore, omega C1 is equal to about 20 radians per second. Which is equal to 1 over tau C1, right? Or it's about 3.5 hertz. Yeah. All right. Tau C2. What is tau C2? So basically you have C2 here, right? And then if you go to the left, let's call this R out, right? And on the other side, basically it's open, right? So therefore it's C2 times R out in parallel with infinity, right? Because it's open on the right hand side, so that's infinity. So it's equal to C2 times R out. Okay, now the question is what is R sub out? Then you have to do this again, huh? The Thevenin, yes? So you apply a test voltage. We have done this many times, yes? So, like this, right? Like this. Yes? Then you have a test voltage here, huh? V test that has I tests generated. So this is R, L, R, C, R, E, R, pi, R1 intervals R2, R squares. Yes? This is IB, and this is beta IB. Okay, so we got everything. So what you're looking for? You're looking for R out, yes? Okay, so R out is V test over I test, yes? So if you look at this node, right? This is the node right here. Okay? So this current is entering, all the currents are leaving, right? So therefore, I test equal to V test over RC plus V test over RL plus beta I sub B, yes? So what you can have on the left-hand side is that you can have this, that, yes, R, E, R pi, and what is this? This is R slash in parallel with R1 and R2, right? Correct? I combine the two in parallel. So, and then what do you have? You have I sub B here, right? So basically, I sub B times R sub pi plus that voltage drop. What is this voltage drop? Huh?
Beta IBR.
Yeah, beta IB times R3, right? That must be 0, right? Now again, the only solution for I sub B is what? Is 0. Otherwise, this equation would not be valid. Right? So I sub B must be 0. Okay, so this is 0, right? Then you put this back, you will find that R out is what? The parallel of RC and R square. So, tau C2, huh? This guy. So tau C2, as I said, is equal to C2 times R out. So that R out is this guy, right? The two in parallel. So I got the 5 times 10 to the minus 8. Oh, you might be wondering what is the unit of tau? Huh? What is it? It's the time, right? So second. This is in the unit of second, okay? Second. All right. Now, omega C2 is 1 over tau C2, correct? So that is about equal to 22 times 10 to 7 radians per second, or is about equal to 3 megahertz. Okay? Right? So now we can sketch the body plot. Yes? Okay, so this is A sub B versus omega. All right, so now you put the plateau here, right? Which is A sub B max. And what's the value? The real value of A sub B max is what? 6, right? 6 is about equal to 16 dB. Yes? Okay, then you would have a drop here, and that is omega C1, which is equal to 20. And you can have a drop here, which is omega C2, that's about equal to 20 times 10 to the 6. Yes? Okay. Now let's try to make sense of this plot, correct? All right? So let's say if I give you a V sub I, V sub I, then V sub I is equal to 1 sine 10 t millivolts. And I want you to give me V sub I. So that is the peak value of V sub I. That is the frequency of V sub I, right? So the frequency of V sub I is 10. So now you come here, right? You need to try to find out what is the voltage gain at omega equal to 10. Then V sub I is simply V sub I times A sub V. Got it? A sub V at 10 and omega equal to 10. Got it? A sub V is not a constant. So what is A sub V at omega equal to 10? We know that at 20 we have 16 dB, right? Okay, now if you go 1 decade below, we know this is a slope of 20 dB, right? If I go 1 decade below, what is 1 decade below, by the way?
2.
It's 2, right? If I go 1 decade below, this is -4. Got it? Because it's 20 dB drop, -4. Okay, but I'm talking about 20, right? So therefore, what I need to do is I can use the what? The octave, right? Octave. So I'm going to drop 1 octave, right? Which is what? 10, yes? And what is the slope per octave? 6, right? So therefore, right here, what you have? 10 dB, correct? And 10 dB in the if you convert this to the real number, what do you get? 20, right? 10 dB is 20, got it? So therefore, it's V sub I times 20. So V sub O you have should be 20 sine 10t millivolts. Okay, so let me give you another question. Now, what happens if I change my frequency? Huh? So V sub I, let's say you put into the circuit is 10 to the 9. 10 to the, let's say 10 to the 8. Okay. So it's 1 sine 10 to the 8 t millivolts. What is V sub I? Okay, at 2 times 10 to the 7, right? We have 16, correct? So how do you get to 10 to the 8? What's the best way? If you have 1 decade above, so you have 2 times 10 to the 8, yes? So what is it? Huh? Minus 4 dB, correct? And then you try to go backward 1 octave, yes? That will become 10 to the 8, correct? So this will become 10 to the 8. So what is this? You need to add 6 dB, right? Because you are going up. So plus 6 dB, right? So this is what? 2 dB. Got it? So basically you drop 20 dB per decade. That will give you minus 4 dB at 2 times 10 to the 8. And then you go backward, right? You use the octave, right? Then that you go back to because divided by 2, right? So it's 10 to the 10 to the 8. And then this is 6 dB, yeah? So 6 minus 4 will give you 2 dB. And 2 dB, I don't know, what's the real number of 2 dB, yeah? Something. Right? So this low is, what is 2 dB in the real number?
Like 1.3.
1.3? Good, thank you. 1.3 sine 10 to the 80 millivolts. Okay?
That dB is also about times 3 for the previous example.
What?
10 dB is about 3, 20.
10 dB is 3. Oh, okay. Sorry. So it's 3. So that's 3 sine. So you got an idea? Yeah? Now, of course, if the frequency is within the bandwidth, then it is a constant, right? The gain, the voltage gain is 16 dB, which in the real number is 6, yes? Okay, we stop here. Next time we're going to do more examples, but this next time the capacitor will be going up, right? So we're going to see 3 capacitors. At the end of the semester, maybe we'll see 4 capacitors.
On the